Alexandrou. Okay, good morning, everybody. Today, what I would like to do is really show you some of the computations that we do using the lattice QCD framework that we introduced yesterday. And what I really would like to do is to also bring you to what we are doing today, so that it's more exciting, hopefully, for you. And Simone will afterwards try to give you some of the practical steps that we do in order to do this computation. So I hope that's okay. As I said, you feel free to stop me and ask questions. We don't have to cover everything. We cover whatever we can. Okay, so this is the outline of today's lectures. I'm going to do Hadron spectroscopy today, and the next lecture will be Hadron structure. So Hadron spectroscopy is an important subject, as I will try to explain. And I will introduce the basic techniques. And then I really would like to go and show you some of the results that we're getting. And in particular, since we have experimentalists and phenomenologists, I would like to really touch a little bit on the exciting things that are happening at LHP and BESI3. Okay, BESI. Right, so the basic techniques. How do we calculate hadron masses? Because we are talking about now hadron masses or excited states. So first, I will be talking about extracting the ground states, which are the easiest to extract. So, okay, after we select our input parameters, as we said yesterday, after we define the bare quark masses and the coupling constant, there is no more freedom. We simulate, we produce the gauge configurations. As we said yesterday, the fermions are gone. We have an effective action. We have the determinant that represents the fermions. And what we do, we generate gauge links U with this action. And I will show you what we have right now. And then these are generic. We call them ensembles of gauge configurations, U. So we have representative ensembles, like you do in statistical mechanics, right? You have representative configurations of your phase space. Right? Here we have representative representation of the U field, the vacuums, the QCD vacuum if you want. And then these are generic ensembles which we can use to calculate the observables that we need. So the ensembles are universal, right? And then we use them to compute the particular operators. So this is the starting point. We need to have the ensembles with the given lattice size and a given lattice space, A, okay? These are the parameters that are input. Okay, yesterday we didn't get to describe the continuum limit, but choosing the lattice spacing is equivalent to choosing the coupling constant, because you can compute a relation between them. Okay, so whether I choose the coupling constant G or the lattice is one parameter. These are equivalent. So this is one parameter that I have to input. Right, so what do I do? Well, I construct a creation operator which has the quantum numbers of the hadron I want to study that acts on the vacuum. So that's how I create a state. It's not the state that I want. It's a state, because if I knew, I would not do a calculation. I would just create it and have it. I create a state that has the quantum numbers of the state I want to study. For example, for the pion, I will use the core content of the pion is a pseudoscalar, so the charge pion is T bar gamma 5 U. And I use that operator acting on the vacuum to create something which has the quantum numbers of the pion. Similarly for the rho, that's a vector particle. This is an interpolating function. That's what we call this, the creation operation, the Hermitian conjugate of this. We call interpolating field, interpolating function. This is to create something which has the quantum numbers of a nucleon, and it's a spinor because this is a spinor. Okay, so, and then it's Kala singlet, that's the Kala degrees of freedom. And it's a spinor because this combination here it's a scalar. Or we can do the delta where we replace gamma 5 by gamma nu, etc., etc. So I act with these interpolating fields on the vacuum. I create at some time, initial time, we said, remember? Then I evolve in time, and I annihilate at a different time with the same operator. Okay? So that's the basic ingredient. Okay, I mean, you can do the exercise. You can go and expand this in the non-relativistic limit and really persuade yourself that this is what you will get, which is the proton wave function in the non-relativistic case. So that's what we use. We use the dominant things that you will have having valence quarks. Okay, so with that, then, this is what I said. We compute the vacuum to vacuum amplitude of creating the pion at time 0 at a certain point and propagating it at a later time at a certain point and annihilate it. So that's what we call the correlation function. The 2-point correlation function is a 2-point correlation function because it depends on 2 points on the lattice. And this integral here, I can put e to the minus I p dot x. This projects to a given momentum state. So here I project to 0 because I want the mass of the pion. Okay, so you can go and, I mean, these are Heisenberg operators. You can go and put in the Hamiltonian of QCD and show, and I will see it in a minute, that this is a sum, or, I mean, this is, you can get the spectral decomposition of this 2-point correlator. Okay, and then how do we evaluate such a thing? Well, we saw it yesterday. I put my operator in. That's my operator that creates the pion, that annihilates the pion. Remember, bilinears, always bilinears in the fields, right? Here they are, one bilinear, another bilinear. I integrate over, I mean, I do the functional integral. I denote this as psi, but these are really my psi's. These are the Grassmann variables that we saw yesterday. They are numbers now, no, not operators. I mean, we have done everything. I integrate out the fermions like we saw yesterday. So this gives me this determinant, which is a function of the gauge fields, the pure gauge field action. And then, as we saw yesterday, a product of the inverse of the Dirac matrix. Remember the formula we saw yesterday, right? Maybe not, but it's in the slide that I will send you. Go, it's a simple exercise, go and do it. I think it's the first step to understand things like this expression here. But anyway, this is what we showed yesterday. We get the determinant and the inverse of the Dirac matrix, which is nothing else as the propagator. But note, this is the fully dressed propagator now. This is not perturbation theory. Here we have all gluons going around, all quark antiquarks going around. The quark antiquarks will come from the determinant. So it's a very complicated propagator. It's a fully dressed propagator of QCD. Okay? Right. So this is what we do. And we have to compute this expectation value, which I rewrote here in terms of G. This is the quark propagator. And of course, most calculations, but not all, are done in the isosymmetric limit. What does it mean? It means that the mass of the U and then D is degenerate, and we ignore electromagnetic effects. Okay? So if I do this, then I can write this thing here because I have an integral of dx3, and I have an x here and an x here as a trace of U absolute value square. Okay, and then this is the expectation value, of course, overall the gauge configuration. That's why there is this sum here. I sum overall gauge configuration, so that does the integral, basically, right? That sum is this integral, and I divide by how many such sums I do. Okay? Is it clear? Right. So this is what we have to do. So it sounds very easy. Let's see. Okay, so here I put in the exponential that I told you, right? And I put the evolution operator. Here it is. So I shifted the Heisenberg operators to 0 time, and I put the translation operator that shifts also the x to 0. So I put this in, and then I put complete set of states of my Hamiltonian. Okay, I put unity. This is unity. This integral here, sum over n, this is unity, because if I were able to solve the full QCD Hamiltonian, this will be my complete set of states. Okay, and then this acts on my states. It gives the energy of the corresponding state, right? So here it is, here it is. And then, of course, I have a sum over n. However, if I let time, the Euclidean time goes to infinity, because I have an exponential damping, any higher states will die out faster than the ground state. Do you agree? So if I have a sum, e to the minus epsilon n, 0 to infinity, and I take out the ground state, right? Then everything else will be, well, it will be 1 plus delta epsilon 1 plus delta epsilon 2, the gap, etc. And in the infinite time limit, this will be 0 compared to 1. Okay? So this is the spectral decomposition that I told you about previously. So I filter out the lowest state with the quantum numbers of the hadron that I'm interested in. Why? Because this creates, I should have a dagger here, this creates a particle in the quantum numbers of H, which is orthogonal to any other state that doesn't have these quantum numbers, okay? So this filters out the quantum numbers of the hadron I want to study. Okay, so this is the results in the infinite time Euclidean time limit. Of course, we never can take the infinite time, I mean, on a finite computer, and we will see what the complication is by not being able to take this infinite limit. Okay, so you see we have an exponential factor, and now if I take a ratio of this correlator, and okay, another comment, sorry. I mean, the energy appears here because I have put here this momentum, okay? So it's the energy and not the mass yet because I haven't taken p equals 0. Here I take p equals 0, so I just do the integral without this exponential factor, and therefore I have this correlator at p equals 0. And what I do, I divide it to the correlator at an earlier time, t minus 1. T minus 1, I should say t minus a, really. But I'm a little bit sloppy. I either should divide t by a, or I should put here a. But you understand, at one time before. Well, if I do that and take this ratio, if I divide this exponential by t minus 1, what will be left will be e to the minus e. I mean, the time will cancel because I have e to the minus down, it will be, so you understand what I mean, right? I divide it, and what is left is the mass without a t, e to that minus mass. If I take minus the logarithm I get the mass of my hadron. Okay, so this is called effective mass. It depends on time, but in the infinite limit, it goes to a constant. So asymptotically, I should see this correlator, this ratio of correlators to go to a constant. So this is what I look for in my simulation, in my analysis. And I will show an example of such an analysis. Okay, so the problem is I cannot really take this infinite limit on a finite computer. I can go very large, yes? No, it has to have the right quantum numbers. Yes. It is important. It comes now. It is very important. Okay, how fast I approach this asymptotic limit depends on my interpolating field. Suppose I knew how to construct the exact creation operator for a state. If I knew, then I don't need to propagate at all because I acted, right? I don't have to do anything because it would be orthogonal to all other states. Of course, I don't know how to construct the exact ground state of my hadron. That's the whole point. But if I knew, I don't have to propagate at all. So how fast I approach this asymptotic limit, how quickly, depends on my interpolating operator. And this is extremely important in realistic calculations because as we will see this in a minute. So give me a minute. But it's important to construct good interpolating to optimize this so that I maximize the overlap with the wave function of the state that I'm looking for. Because then I approach the asymptotic limit faster. Okay? And I will tell you how we're doing this in a minute. Now, here is an example of a correlator as a function of time. And here I put the right units, it's x0, the time divided by a, right? So these are the time. And you see how the correlator behaves, right? It starts higher because it has many sums, and then it decays, right? And now this is my pion, and because I have periodic boundary conditions or antiperiodic boundary conditions in time, right? I have this symmetry at the middle of my lattice. So this is a lattice of 32 or whatever, 32 probably, right? So I have a symmetry around 16, okay? Because I have to, I am on a ring or anti-ring or whatever you want to call it, okay? And therefore, the function behaves not like e to the minus mt, but like e to the minus mt plus e to the minus capital T, which is the extent of the lattice, minus t. So this is a cosh, more or less. If you write it, it's a cosh. So the function, I will have to fit this correlator to this function if I want to extract this mass. If I have assumed that all other states have died out, okay? Or I take the effective mass and fit to a constant. We will see this in a minute. Okay? Any questions so far? Right. So now, some comments. Well, we said already, M effective goes to the asymptotic value. If I have the same interpolating field left and right, then this approaches as monotonically from above. And the reason is because here this becomes an absolute value. If I is equal to j, if I is equal to k, then this is an absolute value square, and therefore it approaches from above, always, the asymptotic value. But if these are different, this is not guaranteed. I generalize because we will see examples where we take a matrix rather than just a diagonal. This should be dagger. Okay, so it always, and this is an advantage because I know how it approaches the asymptotic value. This goes to a constant, as we said, in the asymptotic limit, and this we call a Plateau region where we fit a constant. And as we said, the onset, the length of the Plateau region depends on the interpolating operators. Now, this is very important, and that's why we need to optimize our interpolating fields. The longer I propagate in time, the higher is the noise. Because remember, we are doing a simulation. We are not doing the integral exactly because this is impossible. We generate a representative ensemble of the phase space, right? Therefore, if I do the sum, I only get the exact value if I sum over an infinite ensemble of configuration, which is of course impossible. The larger my sample, the smaller is the error. But I always have a statistical error in every simulation. And this grows the longer I evolve in time. So this is why it's very important to get the signal as soon as possible. Okay? So all correlation functions, these 2-point correlation functions, grow exponentially. The noise grows exponentially, the errors, with t, except for the case of the pion, and the reason is that the pion is the lower state we have in QCD. We don't have anything lowest in mass. Okay, and I have an exercise, try to show that. Try that you convince yourself that what I'm saying is true, and Simone will prove it for you tomorrow if you cannot prove it. Okay, Simone? Right, but try to think about it because this is very important. Right. So now this is to extract ground states. Now Euclidean time evolution is perfect for ground states. It's not so perfect for excited states because I will have to get the next order. And it's not so great for scattering because everything is real. How can I get scattering? So the message is lattice QCD is very good for certain things. So that's why we still need to do other things, right? But for the things lattice QCD can do, it's a very controlled, non-perturbative approach. Okay, so we will see how to extract higher states from a lattice simulation and how to do resonances. Right, so as I said yesterday, if we do one lattice calculation is not enough, suppose I have physical quark mass, and now we do have simulations with physical quark masses, I still have to take the continuum limit, and I have to make sure that the length of my box is large enough so that I don't have volume effects. So all these have to be checked, and this is very time-consuming, okay? But I really have to do that to have a control answer. If the computations are not done with physical quark masses, then you have to do a chiral extrapolation. And for baryons, this is very difficult, and it leads to uncontrolled errors. I mean, for the pion sector or the kaon sector, the chiral extrapolations are more controlled, but for baryons, it's particularly hard. I'm not saying it's impossible if you're low enough in mass, but it's harder than for the mesonic sector. So what are the challenges that we are facing right now? The challenge is to construct, to have methods to construct optimized interpolating fields that maximize the overlap with the states that we want to study. We need to develop techniques to extract excited states. Ground states are much easier. We need to develop techniques to investigate internal structure of hadrons. And we will see some examples. For example, you know the famous XYZ states that have been discovered. We want to know whether they are molecular states or multi-quark states, or how the quarks, the valence quarks are arranged inside the states. We want to develop techniques to study resonances and decay widths. As I said, this is much more difficult because lattice QCD is very good if you have a stable ground state. And at the physical point, and what I mean by physical point, I mean where all the quarks have their physical values, you need to keep the statistical noise small because the noise increases, okay? So that's the current challenges that we have to address in spectroscopy. Okay, so the first thing is to optimize the interpolating fields, and we have developed techniques to do that. Instead of creating a quark at a point, so we create a quark at a point, we can smear this quark field so that it has the right size. So if I combine these three quarks, for example, for the proton, it will give me the RMS ratio that we know experimentally. That's one way to optimize my interpolating field, because I use some physical knowledge to create the initial state, okay? So this is what we do it. This is a gauge invariant way of doing it. I multiply this creation operator at y, with this, what we call smearing function. It's gauge invariant, so it depends on U. And this is a function here. And this results in having a Gaussian distributed function. And then I compute the ground state of this, that this interpolating field combined appropriately creates. And I probe the RMS of that I have as a function of these parameters. I have two free parameters, alpha and S. This is N, and this is alpha. This is this N here, and this is this parameter alpha. And I vary them until I hit the value I want of the, and you see it's pretty flat after alpha equals 1, and this is how many times I repeat the application of this function on this interpolating field here. Okay, so I repeat it many times until I reach the RMS of my proton, half a Fermi approximately. Okay, and then this optimizes the calculation. I will show you examples in the next slide. There are other techniques. I can do it by using applying the propagator. This we know it's a kind of an exponential smearing function that it creates. It's similar. It has some parameters to tune, the mass and the N, how many times I apply it. It's similar. So these are the techniques that we use to improve our interpolating functions. And here I show you examples of what happens. So this is a quench calculation because you see it has very small errors, so you can really see the improvement. This is 550 MeV pions, very heavy pions, quench. Now you can do this on your laptop. It's a very easy calculation. I mean, back then, 20 years ago, it was a big calculation. But you see, if you use an unsmeared source, this is what you get. If you use a smeared source, you cut out the contamination from excited states. And you get these very nice plateaus here. This is the effective mass that you can fit. So you fit this plateau here, and you extract the mass of the pion. This is for the nucleon, you see. So you cut off all these excited states. Okay, this is quench. We no longer do quench calculations in current day lattice QCD. We do everything having dynamical quarks in the C, so the determinant is simulated. And here I show you examples of having the U and the D in the C. It's not on the physical point yet. It's higher than physical. And you see the kind of signal compared to this. Much more noisy. But again, this is the unsmeared, you see, and these are different levels of smearing, and you see that I approach the plateau much faster than I do with the local, although the noise is larger than this. So that's what we do. This is another example. You see, this is the point that we don't do any improvement, and this is the improvements. So, and this is extremely important because we can already fit from very early on. Okay, so this is what we have to do, and this is because much more important if I'm going to do structure, as we will see in the next lecture. Oh my God, it's already, Anyway, I said I'm not going to go fast. I think it's better that we understand what I can cover, and then you will have the lectures and you can go through them. Okay, now this is what I was telling you before. This is quench. We don't do it anymore, but you see, even in the quench, you see all kinds of gluon exchanges. These are all in. Unquenched, we have also all the quark loops. So this is what we are really calculating, propagators that are fully dressed. And it's automatic. If I do the inversion within lattice QCD, this is automatic. Now, how do I do the computation of these propagators? Well, I have to invert the Dirac matrix. Now, the Dirac matrix is a huge matrix on the lattice, but it is sparse. So this helps me a lot. So how do I do it? Well, what I do is solve this linear equation here. This is the Dirac operator acting on its inverse should give me a delta function, correct? So if I put a delta function here and solve this equation, well, this I always apply, it's very easy, then I can find its inverse. So this is what we do on the lattice. But if I do this, if I multiply now by the inverse and take it over here, I will get the propagator from a fixed space and time everywhere. So basically, I get a column of this full matrix. I don't get the full propagator. If I want to get the full propagator, I have to repeat this at every point on the lattice. So this is volume. And this is not what we do. So what we do is we have a fixed point. I solve this linear equation, and then I get a column of this inverse. So I get the propagator from a fixed point to everywhere. Okay, this is what I do. Now, there will be instances that I want to get from everywhere to everywhere. Okay, how do we do this? We cannot invert volume times. This will be a huge, we cannot do it at the moment. So there are techniques to do this. I'm not going to go into a lot of details, but there are techniques to do this using stochastic, what we call stochastic sources. These are, vectors, spinors, that satisfy their sum or expectation value to be 0 over there. So I have n r components of this spinor. If I sum it, it has to be 0. And the product, their complex conjugate, should give me a delta function. So this we call stochastic sources. And now what do I do? Instead of a delta function, I construct this quantity here, phi, and then this propagator is just the expectation value of this phi with this z. Basically, instead of having a delta function here, I have this stochastic source here. I invert it, and then I compute this overlap here, and I have the all-to-all propagator. So I have any y going to any x. Okay. However, this is exact only if this n goes to infinity. So now I have introduced an additional source of error, which is called stochastic noise. So I have two sources of errors. One, because I don't have an infinite number of configurations. And the second is because I don't have an infinite number of stochastic sources. And I have to make sure that I control both of them. So to calculate the all-to-all propagator is much more difficult than calculating from one fixed point to everywhere. But we have techniques now to do this. And there are tricks to improve the signal, because if I have, for example, for the pion, the all-to-all propagator, which are these phis that I create, then I sum also not the end point, but also the initial point, which means I have volume, more statistics. And therefore, my signal is much more improved. So these are the techniques we are doing to get more accurate results. All right. So now the actual simulations. Where are we on the lattice? Here is a plot of each point is a simulation. It takes 2 years or 3 to do. So I give you, this is the mass of the pion, and this is the lattice spacing. And we said we have to take the continuum limit. We have to go to 0. This is the physical pion mass. And you see previously, this is history if you want. We were up here because we couldn't simulate the physical point because of the noise. I told you there's a lot of noise. However, in the last 5 years, all collaborations using all type of fermions that we discussed yesterday, Wilson type, Stagger, domain wall, have simulations right at the physical point for several lattice points. Now, the size of the circles is how big my volume is. And that's why you see, for example, here, 2 circles. It means the same lattice point, bigger volume, because I want to study volume effects. I want to correct for volume effects, okay? So you see that for spectroscopy and structure, most of the collaborations use Wilson-type fermions because it's easier to do the calculation. Very few use staggered, BMW and Milk, and only one uses domain wall. This is in the US and UK, QCD and RBC. So that's why I mention all these fermions, because each collaboration has its own favorite with advantages and disadvantages for each. And these should all give the same result in the continuum limit after you control finite volume effects. Okay? So you see, I belong in the ETMC, European Twisted Mass Collaboration, which are the twisted clover type fermions that I showed you yesterday.
Why are there some points which are below the physical pion mass?
Yes.
The other question is, can you give us a very short feeling of the main collaborations and where they are?
Yes, of course. Okay, remember, in order that I fix the masses, and maybe I will show you this later on, I have to input bare parameters. So a priori, I put a bare parameter. I don't know what the result will be before I do the calculation. So I guess an input parameter, then I compute the pion mass, and I iterate this. And this is expensive. And sometimes I fail to hit exactly, really exactly, the physical pion mass. That's why there are small variations here, okay? I mean, BMW also simulates below the pion mass. I mean, this is not their disability to tune. It's because they wanted to do it, because for some quantities, you want to know the slope. And this is, you know, of course, it gets more expensive if you go lighter and lighter. Because you know, the Dirac propagator has a singularity when you go to the chiral limit. It's 1 over p slash plus n. So if you go to 0, you have a single, you know, you cannot invert it anymore. So that's why it has taken years of developments and algorithms really to get to this point. But that's what you do. That's why you get a little fluctuations from the straight line, from actually hitting the pion mass, because this is an iterative tuning you have to do. Okay. Now to answer the other question. The extended twisted mass collaboration is basically European plus some US components, because some of our collaborators got jobs in the US. So it used to be called European twisted mass collaboration, and now we changed it to extended twisted mass collaboration. It has big components in Italy, Rome, contributes Rome 1, 2, and 3, members of the collaboration. Trento used to have people in the collaboration. And we are very open, of course, to anyone who wants to join us. We have people from Bonn, Desi, Bonn, Desi, who else in Germany? Bonn, mainly Bonn and Desi. Then we have Switzerland. We used to have people from France. We still have one collaborator. That's mainly what it is. CLS is a German collaboration. Mainz, Regensburg, these people. They do Clover improved fermions. BMW is Wuppertal, Budapest, and Marseille. That's what the BMW stands for, Budapest, Marseille, Wuppertal. They do Wilson improve, but they do smearing. Okay, now we're getting into details. The purists only smear the operators. They do not smear the gauge fields that go in the action. Because you need, if you are Lusher, you are very strict, you want to preserve the locality of your action. Smearing the operator in the limit A goes to 0 is fine, because you smear only the spatial, mainly, component. You don't affect the time evolution. Okay? Now, BMW smears the gauge fields that go into the S that they are simulating. This cuts out ultraviolet noise, and it makes the simulation easier. That's why some of the first results that came out, the dynamical simulations, came from BMW, because it was easier to simulate. Okay, JLab, this is an American, MIT, and William and Mary, an American collaboration. Clover, they either do no smearing or they do smearing, it depends. PAX is Japanese. It's from Japan, mainly Keck. And BMW Milk, it's an American collaboration. They do Stargate. They have been doing Stargate since the beginning. And what they have done, which is helped a lot the community, the minute they produce a sample, it's open to everybody to use. So you can just download it and use it. So many people just download those configurations, and what they do, they have the use, which are staggered, and then they do Clover fermions on top. So this is a kind of a hybrid action, okay? We don't do that, but there are many people who do that, because the configurations are available, and as you see, they can simulate. This is a collaboration that can simulate a very coarse lattice spaces. You see, this point here, it's 1.15 Fermi. We cannot do this. We have to go to very small lattice spacing to simulate this. Okay, so you see advantages and disadvantages of the different discretization schemes. Huh? We have to go here to simulate. That's our points here, the 5 ensembles that we have at the physical point. The same is true for these guys. You see, they're here. They have 2, they're here. This is PAX. This is PAX again at the similar lattice space. Very large volume. This is 10 Fermi volume. These are the only people that have this. RBC, UK QCD, I already told you this is an American collaboration together with the UK QCD. There are people from Edinburgh in the collaboration, people from Columbia, University. They have been doing this from very beginning. These fermions have very nice chiral properties because you don't violate chiral symmetry. So if you have a process that is crucial to preserve chiral symmetry, this is an action to use. Okay? Right. So my conclusion is we are now here. So no longer chiral extrapolation, uncontrolled chiral extrapolations. We can really be at what I call physical point. And I am insisting to use ensembles at the physical point because I do baryon structure. And I don't want to have uncontrolled chiral extrapolations. Okay, right. Okay, so this is what I told you right now before. I have to control corrections due to the finite lattice spacing. We have seen that I have corrections that go either linearly in A if I don't do improvement, or with A squared if I have improvement, okay? So if I calculate a ratio, for example, now, this we didn't do because we didn't do the continuum limit. Everything that I calculate on the lattice are dimensionless quantities. I calculate A times the nucleon mass, for example, or A times the omega mass. Okay, so they're dimensionless. So before I fix my lattice spacing, I don't know what the physical value is. So I have to choose one quantity to fix my lattice spacing. And we said lattice spacing is equivalent to fixing the coupling constant. It's one of the input parameters. But if I take a ratio, this is dimensionless. If I take ratio of masses, and this is why I took this ratio here. So what I compute on the lattice is equal to the experimental value plus order A terms, because I have a finite lattice spacing, plus, I didn't put it here, corrections due to volume. Now, the volume corrections for these quantities are exponential, e to the minus mass times the length of my lattice. So if I were purist, I would write order A over some quantity to make it dimensionless, right, P, plus order e to the minus M, the difference in the masses, so ML. Okay, these are exponential. We know for these quantities, the corrections are exponential. So that's why I didn't write them, because I use large enough L. But these I have to control, this guy here, okay? So that's why before I compare to experiment, and that's why I stress this, because some experimentalists forget that. They take a lattice paper, they see a number, they say, it is agrees or agrees. In order to make sure, okay, if I have very small lattice spacing, but probably this is going to be small. But the real thing is to take the continuum limit. This is the program I have to do. And then I can compare to experiment and be sure that you should agree at the physical point, if the masses are set to the physical ones. Now, finite volumes, we use large enough volumes so that L times the smallest mass that I have in the theory satisfies this criterion. So this I can ignore in most calculations, okay, for these quantities. Okay, I said about the masses. Now, this plot, I show it because at the time that it was produced, 20 years ago, it was a breakthrough. It was done in the quench approximation. This is PAX. This is the PAX collaboration. It was done in the quench approximation, but they did the whole program. They took the continuum limit, they corrected for any finite volume effects, and this is what they got. And now that you can compare to experiment, they took the chiral limit, they did all the program. And what they are finding are deviations from the physical masses. Now, I have empty symbols here and field symbols. Now, this shows you how I tune the strange quark mass. I pick kaon, the kaon mass, and I say I will tune my strange quark mass, the input, the pair quark mass, so that it produces the kaon mass. That's how I fix the strange quark mass. Okay? The light quark mass is fixed from the pion. So that's two quantities that I use, right? And this and everything else is determined. I mean, I took the continuum limit, so no problem with the coupling constant. And then I can make a comparison, and you see differences, if I look at the field symbols, differences from the experimental value. What this tells you is how large are the dynamical quark degrees of freedom in the vacuum. So that was an important calculation because it showed us that there are large, of the order of 15% deviations coming from not simulating the dynamical quarks in the vacuum. So that's what this is. It's a very famous calculation and a breakthrough at the time, 20 years ago. Right. So this told us that we really have to go on and include the dynamical quark effects. Because even at the masses of these lower line baryons, these are non-negligible effects. And here I say the scale is set using the raw mass. What does it mean? I fix my lattice spacing, making sure that the raw mass in the continuum limit has its physical value. So that's another parameter that I need to input. So the masses of the quarks and the lattice spacing or the coupling constant. And then everything is 10. Okay. So now I told you about, yes? It's already, oh yeah. Okay. Okay. Yeah, we break. No, Monday I teach.
But you are teaching.
No, I'm teaching on Monday, Angela. Okay. Well, now you have to help me a bit because otherwise I continue here or I go very fast and go to the structure because I don't think we can cover both. It's up to you. So I go very fast here. Or I go fast, very fast here, and then I go to structure. This has died. Oh, no, it's okay, it's okay. So I go fast now? Yes. Okay, so these are unquestioned calculations, the same principle as you see, feed the plateaus, okay, and you extract the masses. So that's what BMW did. There are the feeds. I'm going to go fast. This is an example coming from us, how to fit. This is courtesy of Simone. Okay, he's going to show you how this is done. Very controlled feeds to extract masses. These are our three physical point ensembles. At the physical point, you see three mass values: light, strange, charm. Okay? After I fix these parameters, everything is fixed. I extract the lattice spacing, for example, from the nuclear mass, and I'm ready to go. And these are the continuum extrapolations you see here. You see a slope, but look at the scale. It's a small effect, but still you have to do it. But it's a small effect. So take the continuum limit. It goes like a squared. We said we have another a improved action. And this is now the spectrum, okay? So we saw the quench, now the fully dynamical, perfect agreement with experiment, you see? Perfect agreement with experiment, perfect agreement with experiment, predictions. This is what we would like to do, of course. Not just reproduce. After we reproduce and we have everything under control, we predict things that are unknown. This is the real thing that we do. So this is a very recent work that we did with a student, actually, an undergraduate student did this. It's a diploma thesis. And now this I would like to show you because BMW went further and included isospin corrections. So this corrects for the difference between the U and the D, and it has electromagnetic effects corrected. And therefore, they can predict or get the nuclear splitting between the proton and the neutron and the other, in the other isospin doublets. So here it is, agreement with experiment prediction, okay? And now the interesting thing, you can tell how much comes from the difference on the mass of the U and the D, and how much is electromagnetic. And you see for the proton, they cancel it. They're going in the opposite direction. So this is the kind of thing you can learn about doing such calculations. Okay, this was a science paper calculation about 10 years ago. Right, excited states are harder to do. I'm not going to say much. You can, because we want to go to structure, you can look it up. We do have techniques, but they are much, much more difficult. And most calculations are really done on non-physical pion masses. Why? Because most excited states are not stable. They are resonances. So they decay, and we have to take that into account. So there are open questions here. For example, we cannot see the roper, the first excited state of the nucleon. We cannot see it at the moment. We don't know where it is. So there are a lot of open questions, a lot of things to do. We have to develop techniques, so I go fast, as we said. This is a very elaborate calculation by the Hadron spectrum collaboration. I mean, there are collaborations which just take the configurations from the collaboration that I showed you and do the analysis, do the inversions and do the propagators. So this is a particular collaboration. It involves mainly JLab people and some that now are elsewhere to compute excited states. But you see, everything is done at non-physical Koch masses because resonances are unstable. I mean, excited states are unstable. Only if you have large pion masses, they become stable. Okay, then I don't comment. So excited state, you see, we do have techniques to compute them. And we can also compute exotic states, like, you know, having quantum numbers that are exotic, or glue balls. For example, here is an example where you see a glue ball appearing if I put a interpolating field of a glue ball that creates a glue ball, okay? So these are the kind of things we are doing currently. This is another example of glue balls. You see very difficult interpolating fields that we have to put in, but this is possible. Multi-core states, I told you, there are new discoveries of these particles. We want to understand the internal structure. These are the kind of, these are the usual ones. These are the unconventional ones, if you like. And we want to understand how the structure is. and many people are doing such calculations in order to understand this is a recent compilation from LHB of new states that are being discovered, and this is what Vladis QCD is trying to understand. How do we do resonances? I'm not going to go into. We have techniques to do resonances. So what you do is you compute the energy as a function of the length of the box, and you turn this into a phase shift. This is using the Lucia formalism. I'm not going to explain, but there are techniques to do it. There are difficult calculations, but it can be done. Here is a prototype example of reproducing the width of the raw resonance. Okay, and we have done a similar calculation for the delta, but look at how large our errors still are. Huh? So these are current calculations. They are very challenging, but this is what we're trying to do. The rho and the delta are the cleanest because they are single. They decay mainly to one channel. So we want to understand how to develop techniques here and then go forward. So this concludes this lecture. I'm sorry I went fast, but now I go to the next one. Now I have to stop sharing this one and open the next one. Share. Okay. And now I go to, how do I go now? How do I go now? This I have to, sorry, I have to move a little bit. How do I move this bar now to put full screen? Yeah. Okay, view, full screen. Sorry, I didn't start from the beginning here. Why doesn't I stuck? Why can I not move now? Sorry, guys. Okay, let me go from the beginning. And now I share again. Where is it now? Why do I? It's already shared. It's already shared. Very good. Very good. Full screen. Okay. Now let's see. Does it go? Yes. Okay. So now we do structure. Okay. Basic techniques. Maybe I go fast a little bit. How much time do I have? Half an hour? Okay. So up to now, we did masses, which means we did this two-point function. Here it is. Yes, sometimes I change the convention on my sign. Okay, sorry about that. I had plus, now it's minus. It doesn't matter. So we did this thing. To do structure, I have to have a probe, right? So like I do in experiment, I send an electron, hit my hadron, and see, how it reacts. So I have to couple to a probe, for example, the electromagnetic current. So I need to compute now a three-point function because I have creation, my probe, the current, and then annihilation. Okay? So I have to compute creation, operator, annihilation. Okay, so this is what I have to do. This is what we call a three-point function. I have to compute a three-point function. And I can go even further and compute four-point functions. I need this for certain other things. So the higher the function, the more difficult it is to calculate. Right, so let's see. Introduction to the basic techniques. For example, if I would like to compute f pi, the decay constant of the pion, this is easy because here I have the vacuum. Here I have my operator, and here I have my pi plus. This is basically a two-point function in this case. So if I compute this thing here, I get f pi. Okay, this is basically computing the expectation value of, it's like a two-point function. So this I know how to do. I just showed you how to do it. I fit, again, the asymptotic value. This is the asymptotic value. But now I don't know, I don't want the exponent, I want the thing that is in front of it. Okay, that's the difference, because I want a matrix element now, not the mass on top. So, but anyway, I do the same thing. We will see in a minute. Where is this? Here. To extract this thing, and then using this formula, I can compute the f pi. And here I show you, actually here I show you a ratio of the k on decay constant divided by the pi on decay constant as a function of the Koch mass, because I didn't do this calculation at physical point, extrapolated to the continuum limit. And this is using twisted mass samples, and this should be not equal 1. 2 plus 1 plus 1. It means I have the light quarks, which are 2, plus the strange, plus the charm. It's 2 plus 1 plus 1, because the u and the d is degenerate. Okay? So it's 2, I have to correct that. It's not a, it's a plus. So 3 lattice spacings, continuum limit, everything looks fine. I get the experimental value, so this is the point here. It should be at 0. I mean, this is what I, no, this is the physical. No, the physical pion mass is here. So this is the physical value. So I hit it, huh? Everything is fine. Okay? So how do I compute now genuine 3-point function? This is the nucleon. I create a nucleon, I have a probe, for example, the electromagnetic current, I destroy it. Okay, now I have 2 sums to do. I have a sum here, this is fixed, we said. I can compute the propagator from a fixed point everywhere. That's what I did with the 2-point function. So I was able to sum here, okay, to project to a given momentum state. Now, however, I have to sum over the insertion of my probe. So I have 2 sums to do, this one and this one. And this then is the all-to-all propagator. So I can compute this one going here everywhere. I can compute this one going everywhere. But here I have the all-to-all propagator. Okay? Either I use stochastic sources and I introduce additional noise, or I have to be clever and develop a method. And we have been clever. So what we do actually is construct what we call sequential propagators. So what do? There are 2 things to do. Either I take this forward propagator and sum it here, and then use this to invert again. So instead of using a delta function, I use the combination on this linear equation that I told you. Instead of having, remember we had d in g equals a delta function. And I solve this equation to find the inverse. Now, instead of putting a delta function on that side, I put for this propagator that I compute, which, where is it? I don't see it anymore. It's very faint. Are there batteries? So I use this forward propagator, which I have from fixed to all, some to put my current, so I have to fix the current. It's a fixed current that I put in. And then I use this to invert again, and then get the propagator that goes to everywhere. Okay? So in fact, what I do, I compute this line going everywhere. This is called fixed current, Ah, yeah. Okay, okay. Now I have a weapon. Okay, so I compute. This is very good, actually. I like it. This is the old-fashioned way. So I fix the current, so it's called fixed current, and I compute the line going everywhere, and then I bring the other two propagators and do the sum. Okay? So that's how I compute it. Or what I can do is compute this one, combine it with my final state, so I have to fix now my final state, and use that to invert to get this propagator going everywhere. And then I put the current. And I'm free to put any current I want now. And then I combine it with this one that comes from here. This is called fixed sink approach. Fixed source, fixed sink. Okay. The advantage of this is that I can put any probe bringing any momentum. So if I want to compute form factors as a function of the momentum transfer, this is the choice that I have to do. If I want to put here a variety of states, not just the nucleon, then and compute for a single momentum or a single current, single momentum, then this is the choice. But usually this is what we do in real calculations. So now, can I go forward? Yes. Okay, so this is the details of the technique. You can read it, how we compute it. Is what I explained to you, how we compute this 3-point function. Okay? Okay. Now, besides this, which we call connected in the non-perturbative sense, not in the non-perturbative sense. Huh? This is connected because all the valence quarks are connected. This is called disconnected because I have a quark loop which is disconnected from this. Now, in order to compute this, I need to sum here, right? So this requires to have the all-to-all propagator. And this is difficult. This is why these diagrams were neglected for a very long time because they are very noisy, because they have vacuum loops, quark loops, and because technically it's very difficult to compute. Now we have stochastic techniques to compute them, and we do compute them. So we compute everything, okay? Right, now I go forward. Now this compares the two different methods. You can read it. This is a new one. Well, I like this kind of pointer. Okay. Quit. Right. Very good. So this compares the fixed current technique with the fixed sink technique. You can read it, their advantage. Oh, I told you already. Okay, so the simplest thing we can do is calculate the form factor, the electromagnetic form factor of the pion. Here is my current. I have a gamma mu here. So I have to compute this matrix element with a gamma mu. Isobvector combination. And if I compute this matrix element here, I get the form factor of the pion. Okay, we do a lot of techniques. We can also use, on the lattice, we have the momenta discretized. There are multiples of 2 pi L because I have periodic boundary conditions around the lattice in the spatial direction. So I can only access 2 pi over L, 4 pi over L, 6 pi over L, etc. If I want to access different values, I have to do, there are techniques to do that by changing the boundary conditions to get smaller momenta, okay? I'm not going to describe it, but this is what we do. We change the boundary condition instead of having e to the 2 pi L to having general theta. So we have different momenta on the lattice. So we can probe lower momenta if we want to. I told you that we preserve exactly the word identity related to the electromagnetic current. So we have a conserved current on the lattice, so we can use it, and therefore I don't need any renormalization constants, right? This is preserved on the lattice. But even if I needed to, I can compute it. We have techniques to compute renormalization constants. Right, so this is the result. This is our calculation. What I'm showing you here is the electromagnetic form factors versus Q square. You don't see it, but it's versus Q square. And F equals 2, which means I have only the U and the D, not the strange in the vacuum. And the lattice, the lattice results is the band, and you see very, very good agreement with experiment. Okay, so we know that at least we are doing our job correctly. And you see that we get a lot of, it's important to have points at small momenta, because if I want to compute the radius, the RMS radius of the pion, this is given by the slope as I take Q square goes to 0. So this is important to have, that's why it's important to have points at low Q square. Okay, having reproduced the pion form factor, I want to go on and compute other things like the electromagnetic form factors of the nucleon. Okay, this is very interesting because we know now results deviate from what we knew before. So we know that the ratio of the electric to magnetic form factors are not going to a constant, they're decaying like this. And this is what we want to understand. However, notice that the momenta go up to 6. And what I will be showing you, we will be going up to 1. The reason is, the more I boost, the more noise I have, the larger the cutoff effects. So these are the challenges. We need to develop techniques to go to higher Q square, because otherwise our results get very noisy at large Q scale. These are the challenges. And here we need theoretical improvements, not just computational resources. Okay, so this is the matrix element of the electromagnetic current that I want to compute, the nucleon the nucleon matrix element, which is given in terms of the Pauli and Dirac form factors, F1 and F2, which can be related to the electric and magnetic form factors. So now what I have to do is go and compute this matrix element. This is a 3-point function that I told you. You have seen the diagrams. They're connected and disconnected contributions, which I need to compute. This is a big calculation. It's not, it's a big calculation because I have to invert the Dirac metric, which is a big matrix, do these sequential propagators, and have enough statistics to have everything under control. So this now takes as much time as to simulate one ensemble. It's comparable, the time now that we need. So it's a big calculation. You need a very careful analysis to get these quantities. Now, the electromagnetic form factors we know very well from experiment. This has been going on for 50 years. There are a lot of accurate results. If we can reproduce the electromagnetic form factors, then we can predict other things that are less known experiment. That's the goal. Huh? And one of them is the axial form factors. The axial form factors are not well known at all experimentally, and these are very important for neutrino physics. So if lattice QCD can give us these form factors, this is very valuable input for phenomenology and experiment. So, and the technique is the same. If I compute the electromagnetic matrix element, I can compute the matrix element, the nuclear matrix element of the axial current. The technique is exactly the same on the lattice. And I can do it for any current insertion, right? I told you, if I use this sequential fixed thing, I can put any current I want. I can put the electromagnetic, I can put the axial, I can put the tensor, the scalar, I can produce everything on the lattice. So that's the goal, that's what we're doing. But it needs a very careful analysis to extract each matrix element. I can do generalized pattern distributions in the same way, because it's a different insertion, it's a different operator. I can get it all out, okay? Right. So now you know all this. You are phenomenologists, you are experimentalists, you know how to compute pattern distribution functions, maybe. If you don't, then everything is here, okay? It's a, you know, the difficulty with this quantity is that this is a light cone correlation function. I create a quark, the path order exponential, and I annihilate it later on. So this is a matrix element between a proton with momentum p and a proton with momentum p prime. It's a light cone expectation value. I cannot do it on the lattice. Why? Can anyone tell me? Let's see. Can anyone tell me why I cannot do this on the lattice, this matrix element? Anyone? Huh? In Euclidean, I'm in Euclidean space. How can I do a light cone matrix element? I'm at one point, x equals 0, x squared equals 0. I cannot move anywhere on the Euclidean lattice. So I cannot do such a matrix element. So for many, many years, we couldn't do that. However, I can expand these operators in terms of semi-local operators, any derivatives, right? I can expand twist to operators with some coefficients. In terms of such operators having any covariant derivative, Q bar Q, any covariant derivative, these matrix elements I can do. These are the moments. Okay, these are the moments, so I can compute the moments of distributions. And therefore, in principle, I can compute this matrix element on the lattice. Of course, practically, I can only do the lower moments. Can anyone tell me why? I can do 1, 2, 3, and 4 in these indices. I can only go to n equals 4. Why? Because I have mixing. After I have more than 4 indices, I cannot take 1, 2, 3, 4 to avoid mixing. Then higher order operators mix on the lattice, and I cannot really normalize them. So I'm limited to the lower orders, but that's very important because, for example, I can calculate the momentum fraction carried by quarks in the nucleon or in any hadron. Okay, this we can do. This we can do by calculating the matrix elements of these operators in nucleon states. Okay, I can expand these matrix elements in terms of Lorentz invariant function, like I did for the form factors. For the form factors, it's a special case. It's n equals 1. I don't have a derivative. I have gamma mu. I have gamma mu only. This is 1. This doesn't go further. And this will give me the form factors in that case. I can generalize that to 2, to 3, and these are what is called generalized form factors. And this I can compute, like I can compute the form factors in the same calculation. Okay? Right, so this is what I say. I can compute, these are the form factors for n equals 1. I can do n equals 2. And these are very important because I can get the momentum fraction in the nucleon. I can get the spin, the total angular momentum carried by quark in the nucleus, and I can check the momentum sum, right? And of course, if I add everything, the quarks, intrinsic spin, the angular momentum, the total angular momentum of the gluons, I should get 1/2. Why is this important? Because we had a very famous experiment that was done at CERN in 1980, which showed that the valence quark only contribute 1/2 of the spin of the proton. And this was called proton spin puzzle. So if in lattice QCD we can compute this, we can check what is going on. Right. So I'm not going to go into this. Right. So how do we extract this matrix element? Well, it's very similar to what we did for the masses. Remember, we took ratios of correlate two-point functions, and we had the effective mass, and we fit it to a constant. Well, I do the equivalent thing here. I take a ratio. It's a more complicated ratio, but it doesn't matter. I take an appropriate ratio, and asymptotically, this will go to a constant, asymptotically. But now, I have creation annihilation, a time in between. I cannot, this time cannot go to infinity, right? Right? It's not, so what I have are plots like this where I search for a constant in the middle. But you see, this is much harder now. These are different time separations. And you see, I have to make sure that these converge. So it's a much more difficult analysis, but the principle is the same. I have to make sure I'm getting rid of excited states and have the appropriate matrix element that corresponds to the ground state. Okay, so that's the analysis I have to do for each one of these. And it's demonstrated here. Okay, so let's go on. So a first quantity that we all lattice, you see many lattice collaborations, a lot of points. This is flag. This should have been slash bullet, but never mind. This is this matrix element of the axial. If I take the axial current and compute at zero momentum transfer, I get the axial charge of the nucleon, GA, which is very well known from double beta decay. So this is what I have to reproduce first to be sure that I know what I'm doing. And that's why a lot of collaborations worked on this. And this is our latest number. This is like the GTP for lattice QCD. This is the FLAC, what is called FLAC. If you want to look lattice results, go to the FLAC report. It's published every 3 years or so. And it accumulates all the lattice calculations that are published. And you see a lot of points. And the band is their best average of all these results. And this is our latest value, and this is experimental value, and you see that everything is consistent. But this took many years of development to get here. Okay, because you have the continuum limit, you have to do the whole thing. So we do get GA correctly. And now we go further. So this is an example of our latest work on the electromagnetic form factors. And you see the 3 ensembles, the continuum extrapolations, and this, so this is the proton, the neutron, disconnected are computed, so we can separate proton and neutron. And you see that, for example, for this quantity, where data are not so good, lattice has very good predictions, okay? And these are the extracted quantities compared to other lattice people and GDP. And you see that more or less we reproduce all these quantities on the lattice. So with this knowledge now, this is actually this is from Lattice 2024 in the summer. So having demonstrated now that we can get the electromagnetic form factors, we can go and get the axial form factors. So these are the axial form factors. This is how our work compared to the MINDS results, CLS. These are CLS configurations, perfect agreement after taking the continuum limit. And this is a pseudoscalar where we really don't have experimental data. So these are predictions now coming from lattice QCD. And this is my favorite picture. This is a decomposition now of how much of the spin is carried by who in the proton. Okay, so here is the U quark, then the S, what these lines here are the connected, and this is the disconnected. So you see, C quark contributions are important. You cannot ignore them. Gluon contributions are important. So if you add them up, you do, of course, recover 1/2. I mean, quantum mechanics work. Now notice, all these numbers depend on the scale and on the renormalization. This is a 2G VMS bar. So these numbers, in some sense, are random. If you add them up, they should give 1/2 in whatever scheme. Okay? So this is quantum field theory. This is quantum field theory. This is, you know. So we do now understand why EMC had half, because it only probed this much. Okay, which is half. It's about half of 1/2, from 4th. So we can now understand what is going on, right? So this is my favorite slide to see what lattice, to demonstrate what lattice QCD can give us.
So can I ask you?
Of course.
Something from someone who doesn't know.
Yes.
So is it understood why the up quark gets much more, provide much more?
Well, Alejandro, I don't know. This is phenomenology. This is the numbers I get. How do you explain it?
I mean, physically, does one understand?
I don't know. So this is G, so that's the total angular momentum. So it's the sum of orbital and
Yes, this is the sum of orbital. The orbital for the D is negative. It's opposite from the U. So if you add it, it subtracts.
No, but why the up as more than?
Well, the angular momentum for the R is positive. The angular momentum for the Tau, I don't have the plot, is negative.
Okay.
So one adds, the other one subtracts. But I don't know anything better explanation.
the observation that the contribution of orbital angular momentum of the now is opposite.
But
See, I mean, if you probably can
this up and down of opposite sign, let's say.
Yes.
Angular. But is this true in any?
In the proton, this is the case. You see the U, there are two U's, right? There are two U's in the proton and one D. And one U, it's a spinor, and the other one coupled to a scalar. So in some sense, they are different, right? Yeah, but Angela, the U and the D are different, right? We agree in the proton. They couple differently, right? And we know that the angular momentum of one is positive and the other is negative. So this we know. So there, it's not a surprise that they behave differently, let's say. Okay? I think it's not a surprise because.
Details are telling us something highly non-trivial about QCD.
Okay, so now in the last minute, okay, I told you that we cannot compute light cone matrix elements. And so for a very long time, we only computed moments, lower moments. Now we really can compute the full GDPs. And this is due to theoretical developments, due to G that had a brilliant idea. I don't have the explanation here, but basically, instead of computing light cones, matrix elements, you compute spatial matrix elements, and then you boost to high boost. So you approach the light cone, you boost your nucleon state so it approaches. Of course, it doesn't really go to the light cone, but you know if you boost and you are close to the light cone, you can do perturbation theory, and you can compute perturbatively the matching, this kernel here. So you can compute on the lattice spatial correlation functions, boost them. You have to apply a boost, so it's a non-trivial calculation of the lattice. And then you get the physical ones by applying a perturbative matching, provided the boost is large enough compared to the nucleon mass and lambda QCD. Okay? So now we can compute these matrix elements. And look, on the lattice, it's the same. Instead of having a local current now, I have an extended operator. Here is a Wilson line. This is an extended operator, but the techniques are the same. Of course, the renormalization becomes much more difficult because we have non-local operators that we have to deal with. But the lattice techniques are the same. Like I compute the electromagnetic form factor, I can go and compute this. This is a disconnected. This is a Kluman contributions. I can go and compute them and get the generalized parton distribution function as a function of x. Okay, so this is what we are doing at the moment. These are much harder calculations. It's only at the beginning. We are here how we were in masses 15 years ago. That's where we are. So it would take another, we have to really develop a lot of techniques. And therefore, let me conclude here by saying that we can do a lot of calculation now in lattice QCD. We still need the development of techniques to do them. So a lot of theoretical work is also being done. Also a lot of algorithmic work is being done. New ideas, we need to have them. And therefore, I conclude by acknowledging my collaborators. Here are all these members of the Twisted Math collaborator. Here is Simone. These are the groups that are contributed, and of course we welcome everybody to join us and contribute. And I stop here, thank you.